Hello, and welcome to CNC Beginner's Guide. My name is Stephen Thompson. Today we're going to be going over how to create digital tool libraries in the Manufacture Workspace in Autodesk Fusion. Now, having really good digital tool libraries is kind of the first step in creating good CNC programs, and making sure that that digital tool library matches exactly whatever physical tool library you have in your workshop that you're using on your CNC machines. Matching those two things up is really key. There's a lot of details, but yeah, why don't we get started? So to get going, we're going to first be talking about a tool library that I made for my book, CNC Beginner's Guide. And the I made a couple tool libraries specifically for this book that we can use in like kind of the sample projects that we're going to be working on. And if you take a look in chapter 5, I actually go over in great detail a bunch of different things about tool libraries, stuff that we're not even going to kind of get into today. Today we're just going to be talking about how to use the software to make tool libraries. But if you want to go into any more detail about any of these things, you can find it in chapter 5 of the book. And if you go to the appendix of the book, we can see I have here a couple tool libraries for the book. Now, I made two tool libraries, one for a Haas VF2 mill and one for a ShopBot Alpha router. Now, we're going to make some tools today for the Haas VF2, but it's the same process for making tools for a wood router. At least in Fusion it is. And, even the tools that I'm going to be making today that match the tool library for this book, they're really just for practice. When you make your tool library for your programs, they're going to have to match whatever library, actual physical tools you have on hand. And they're probably going to be different than our tool library. And the machine you have is probably going to be different than this exact mill. So the settings are going to have to be a little bit different. So this is really just a starting point for what you're going to be doing on your own. So if we take a look here in the appendix of chapter 5, table A13, here is a detail of the Haas Mill VF2 SS tool library for aluminum specifically. And here I have tool geometries, tool information, and then I have feeds and speeds information down here as well. So we're going to use all these things to build a digital tool library. At the very bottom here, I have a note on, the machine itself. So for the Haas VF2, I know the max spindle speed, I know the horsepower of the motor, the X travel, the Y travel, the Z travel. All these things are really, they're going to kind of like guide the choices that I make during the CNC programming. But let's get going in Fusion. So if you open Fusion, if you go switch from the design environment or design workspace to the Manufacture Workspace, if I go to Manage and I go to Tool Library, and we talked about this in the previous video when we kind of did the overview of the tool libraries, we have here documents, and if you had any open documents that you were working on that had tools in the CNC program, they would show up here, separated by the documents, but we don't have any yet. Then there's the cloud, which we showed you in the last video how to turn on your cloud libraries. You basically go to preferences here and you enable cloud libraries. Then there's the local if you want to save them locally, and then there's the Fusion samples library and the vendors libraries. Okay, so there's a lot going on here. Let's just start by making our own cloud library. So I'm going to right click on where it says cloud and say new library. I'm going to type in here CNC Beginner, and I'm going to type in Haas Mill, or I'm going to type in Haas VF2. Okay, and hit enter. So now I have an empty tool library. And there's a few ways I can add new tools to this library. One is I can click the plus button up here at the top when my library is highlighted, click plus, and then I can kind of go through step by step adding a tool So let's start with that. If we take a look at the sample tool library again, our first tool here is an 1/8 inch flat end mill. So let's add that one. So go back to Fusion, milling, I'm going to choose flat end mill. And description, I'm going to say 1/8 inch flat end mill. And the vendor, I can get that again from the appendix. The vendor is AccuPro, and the product ID, I'm just going to copy that. And let's put it in here. AccuPro, product ID, paste that in there. And if I had a link, you could find it there. You can go to the Manufacture website and get details about this tool. You could do an online search for that as well, and you can put a link in here in case you need to order any new tools. Now let's go to the cutter section. The cutter section is where you define the kind of geometric details of the tool. Most of these numbers don't change. Type is flat end mill. Units, I'm going to change this to inches, and that's because you could work in millimeters, but all of the details of this tool are in inches, so I think it makes sense to work in inches. Let me see. We have 3 flutes on this tool. Overall length are 2 inches, so I'm just going to kind of work back and forth. So number of flutes, 3. This one's actually quite important because it affects the cutting data. The material for this is carbide. Diameter is 0.125 inches. There we go. And the shaft diameter is the same for this tool. Overall length is 2 inches. Let's go back and check. Overall length. Shoulder is 0.5 inches and the flutes are 0.5 inches. Let's go back to Fusion. Shoulder is 0.5 and flute length is 0.5. Okay, so that's looking like our tool. The length below holder. Now this one's really important and it's highly variable because this just depends on the position the tool is in when you tightened it in the tool holder or the collet, and that's going to change. We know a few things about here. We can't go more than the overall length, and we can't go less than the flute length or the shoulder length. So it's got to be more than 0.5, less than 2. And the trick here is really, you don't want to be clamping on the flutes. You want to be clamping just a little bit beyond. So the kind of rule of thumb that I use is about 1/8 of an inch to 1/4 of an inch below the flutes. And that, kind of depends. Sometimes you have tools that have like a small flute section and a longer body section. But for this tool, I know that I'm going to have it be about 1/8 of an inch outside or beyond the flute length. So I could say 1/2 an inch plus 1/8 is 0.625. And notice you can see it changing over here in the preview. And I can zoom in and zoom out, and I can even orbit in this preview if I wanted to. I can click the home button here, and it brings me back to home. So this number 0.625, again, that's not exactly what it's going to be. The important thing to note is that it has to be at least more than this in order for my simulations to not show, like accurate relative position between the tool holder and the part geometry. Yeah. So we'll leave it at that, and we can make a note. A good thing to do is to make a note when you're putting your tools in, or where you have your tools in, that the length below holder has to be a certain number, and then you can kind of aim for that. But know that it can be your actual part stick out or actual length below holder can be a little bit longer, but it shouldn't be smaller than this number. That's kind of that's it right there. Okay, so moving on to the shaft. Now our shaft, this tool doesn't have any kind of differing shaft geometry, so we're just going to kind of leave it as is. But if your tool got like wider and was a different geometry up here, it had a slope to it, you can add that by adding upper, lower diameters and heights to the shaft. It's something you got to play with. It's a bit tricky, but you can get there. Okay, for the holder, now this is kind of a tricky one because you want a pretty good holder. You want a holder that actually represents whatever tool holder you have, but it may not be here in this section. So you may have to make one from scratch. The way you'd make it from scratch is you'd actually go back to the tool library and add the tool holder geometry in there, but you might be able to find something in here. So there's something I found in here a little while back where it was ER. I know that the tool holder that I have for this is a ER32, and I believe that there's a sample of that one in somewhere in here. Let's see. Hold on a second. So actually I think that I found the tool holder that I wanted in the samples library, so I can show you how to add that after. We're going to come back later and add that. But let's go to the cutting data section for now. And let's add some of this information in. So I'm going to go back to the appendix here. I can see that for my 1/8 inch tool, my surface feet per minute was 393. But this is really kind of like, this number is defined by like your cutting tool type, your in this case, which is carbide, your type of machining, which in this case is milling, and the type of material you're going to be machining into, in this case aluminum. So I chose a number in the range there, which is 1,000. Now the reason that we can't have 1,000 surface feet per minute for the 1/8 inch tool is because the spindle speed depends on the diameter of the tool, and if we were to calculate the spindle speed using 1/8 inch tool with 1,000 surface feet per minute, we would get a number here that was greater than 12,000. But 12,000 is the fastest that my machine can spin, so I can't go faster than that. So that's why this number right here is lower, because 12,000 is the max. So let's go back and let's see what we got here for Fusion. I'm actually going to create a new preset. That's what I'm going to do. So under cutting data, you can add the plus button here. I'm going to do a plus, and I'm going to call this one aluminum. And hit enter, and that is because these numbers that I have provided are for aluminum. I can delete the default. Yeah, so we just have the aluminum one. Great. So spindle speed, I'm going to set that at 12,000. And I see that my surface speed is calculated automatically at 392. Ramp spindle speed, I'm going to keep the same as the actual spindle speed. Now, cutting feed rate is, if you look in the appendix, we can take a look at those those kind of equations. Let's see. Let's go up here. Yeah. So spindle speed is 3.82 times surface feet per minute divided by the diameter of the cutting tool. Feed rate is the spindle speed that you calculated up here, in this case 12,000 RPM, times the number of flutes, which stays constant, times the chip load. So feed rate will be calculated once we enter the chip load. So let's take a look at the sample tool library again, and the chip load for our 1/8 inch tools. So milling feeds and speeds, 1/8 inch tool, chip load 0.0007. Okay, so let's go back and type that in. So if I feed per tooth is also called the chip load. So right here it's at 0.001, and ours is 0.0007. And then the feed rate should be calculated to 25.2. go back and check our library here. Feed rate 25. Yeah. Flutes. Okay. So let's take a look one more time. Okay, so we set our spindle speed. We set our feed per tooth, or also known as our chip load. And then all these numbers, we can leave these separate feed rates as the same as the original one. Notice there's a little FX here next to it, and that's means that it's controlled by an equation. So we see that in the equation it's saying tool feed cutting, which is just the number up here, the cutting feed rate. So if you could write equations in here, and you could reference different values if you knew all the different things here. You can make little functions in here. Okay, ramp feed rate and ramp angle. I don't think I have those specified in here. Yeah, those are the defaults for those are probably okay. And and this is kind of something that you'll see is that if when it's ramping, you'll notice that it's ramping at a slower feed rate, and you can see the degree at which it ramps, and if you need to make any changes to that based on what's happening in the machine, that's what you would do. So really, for all of your tool libraries, this is a great starting point. It's like, okay, these are numbers that I know work on some machines with certain capabilities, and I'm going to try. You try them on your machine and see how they kind of see what the results look like, and then you make changes to your feeds and speeds based on what's happening in your specific machine, because it's so machine specific. Like I know that this works for a Haas VF2 SS with a 30 horsepower spindle, which is a pretty big mill. I mean, they make mills that are much bigger than that, and they make mills that are much smaller than that. So this is kind of like a mid-range mill. So these values will be too much for some machines, and they will be not enough for other machines. Part of it is, it gets a little more complicated because part of it is what the machine's capable of, and then the other part is what the actual tool is capable of, because at some point you're going to break this tool, and this is such a small tool that even a small mill can break this tool. So with the larger mills, you really kind of bump up against the capabilities of the machine. With the smaller tools, you're more likely to break a tool before it really affects the functioning of the machine. Okay, for plunge feed rate and plunge feed per revolution, we could take a look, but normally you're not actually doing a lot of plunging with end mills. This is more for like drill bits and things like that, but you can do some plunging. So let's see what we've said here for drilling feeds and speeds. Plunge feed rate 28 for 1/8 inch tools. Let's take a look. Plunge feed rate 13, which is slower than the feed rate that I have in the other one, so I'm going to leave that for now. If this is like really, really slow for some operation that you're doing, you can increase it, as long as you're getting good results in the machine. Okay, this other section right here, using step downs and step overs, is pretty nice, and we can take a look in the appendix where some of these values might be. Okay, let's take a look at found it here. In the appendix, under page 273, tables and charts, in the appendix, I have a chart here that is a rough starting point for maximum depth of cuts at full tool width. So this is a maximum depth of cut recommendations for carbide cutting tools of different diameters and a variety of materials. And then there's a graph of it. So let's take a look. We have 1/8 inch tool, and these are really just starting points. Like there's so much variability in machining situations that I try to get numbers that were like really mid-range, right? So these might be a little bit too much, but they're not going to be crazy too much for your machine. They might be not enough for your machine, or you might be able to get away with more, but this would be ideally a good starting point, and then you respond to what's happening in the machine. So if we look at 1/8 inch tools and we go to aluminum, I have 0.04. These numbers, I have to say, when I was learning CNC, figuring out what good values for these numbers are was very, very challenging. And it took a lot of trial and error. And it's machine specific, it's tool specific. There's a lot of kind of variation, which is why it's hard to nail down a number, but I think these are good starting points. So we have 1/8" tools in aluminum, maximum depth of cut. A good starting point is 0.04 or 40,000ths of an inch. So if we go back to Fusion here, we can say use step down, and we can say 0.04. And that will show up when you're in making toolpaths. There's an option for step downs. When you do that, it'll kind of automate or kind of populate that value automatically based on this number here. And for step over, this is a little bit tricky too, because this is for maximum depth of cut at full width, which is 100% step over. So what do we set the step over as? Really, when you think of like step down and step over, we think of like this combination of the two numbers create like a volume of material removal. So it's not always the case. You could be working at 100% depth or 100% width or full width of cut. Usually you'll be working at some fraction of the width of cut. So down here, use step over. We click use step over. And for this value, it's really depend on what you're doing. So if we're doing aluminum, a good kind of very conservative rule of thumb is you could do tool diameter, and I'm going to make a little equation here. So I'm going to type in tool, and these numbers come up. So I could say, tool diameter, and I can write a little times, a little star, and I'm going to say 0.25. So a quarter of the tool diameter is like a pretty okay, generally a pretty okay step over starting value. So you can see that it calculates that up to 0.031. Yep, so that's just kind of a starting point, and you're going to have to modify it based on what your situation is. Okay, next section is coolant. Right here we have flood. This is really based on the capabilities of your machine and the type of material you're machining. So if you're machining wood, you don't have any coolant because you can't cut wood with coolant. Or maybe your machine doesn't have flood coolant, maybe it has mist or air through tool or air. But we're going to say that this coolant has flood, but just make sure you just use the one that works with your machine. Okay, so that's it in the cutting data section. We have good cutting data which is like a starting point for aluminum. And as we use the machines, we're going to change these numbers based on the results we're getting. And then that's how you're going to refine your specific tool library, right? And it takes time, it takes trial and error, and you have to really pay attention. But it's a very very valuable thing to have and a very valuable thing to do when you do it. Okay, the last section is post-processor. And this one's quite important, actually. There's comment. You can write a comment here. It'll write it into the G code if you want to. But the tool number is really key because the CNC machine uses this number, the length offset, diameter offset, in the G code where your G code interfaces with your machine. So it's going to call up tool 1 if this tool is number 1, and if the tool you have registered as number 1 in your machine is a different tool, it's going to use that tool. So numbering tools and your numbering convention for your tools is very specific to your setup, your machine, and your situation. Some machines can recognize 100 different tool numbers, 200, 300 different tool numbers. Some machines can only recognize 20 different tool numbers. So one thing that you can do, and I've done it both ways, I have had it so that my tools, I've set up tool libraries such that the tools have set tool numbers that don't change, 101, 102, 103, 104. But then I've had it where the tool number gets added to the tool as I add it to the program. And that way, my program will always start with tool 1 and then tool 2 and then tool 3 and so on from there. So I like that version. You do whatever you want, however you have your shop set up. But in order to have the software give the tool number as you're adding it to the program, you have to put a 0 here for the number. And then it should add tool numbers as you go. Getting tool numbers just right is really important. We're going to go over that later in the series. Okay, so tool number, comment, and yeah, if your tool does a manual tool change, you check this, but the machine I'm using has an automatic tool changer. Live tool means the tool is spinning. It's really just for use with lathes. Break control is if your tool has this option, if your machine has this option of checking to see if a tool broke after the tool path. It'll check to see if it broke before moving on to the next tool. So we're going to leave that unchecked and just have live tool checked. Okay, so click accept, and we have our first tool right there. 1/8" tool. It doesn't have a tool holder, and it looks like that tool holder that I was playing with this one earlier, that one got added to the tool library. So I'm gonna delete that tool holder that you probably don't have it in there, and I'm gonna go look for another tool holder that I know is something that I have. So actually, if you go to vendor, I believe I'm gonna go down to Haas holders, and I can look for one that matches. So I know that I have actually, this is a tool holder that I have. It's a BT40 ER32, call it. So you can actually look for, if you can find it, if you can find the tool holder by the manufacturer or in the samples library, that's a great way to use it, because what you can do is I can right click copy holder, and I can go up and I can go to CNC Beginner, right click, and actually once the library selected, then I can right click in here and I could say paste holder. And then I have my ER32, call it, and if I go back into this 1/8" tool that I made, I can double click it, and I go to holder. I can say, see holders, CNC Beginner right here. So in my CNC Beginner Haas VF2 library, there's my BT40 ER32, call it. I can say select holder, and it applies that tool holder to this. And I click accept. And there it is, my 1/8" tool with a tool holder and with the aluminum preset, right? Now, if you had different material, you can add presets down here. You can copy and edit presets from elsewhere, and you can kind of get a list of materials going here. Not every tool will work with all materials, but some tools will work with a range of materials. So this 3-fluted carbide end mill will work with aluminum. It'll work with brass. It's not going to work with steel very well, but for the softer materials, it'll work with aluminum, or it will work with plastics pretty nicely. So we can do that. Okay, the other thing I'm going to do right now, well, I guess what I'm going to do is I'm going to keep working on this, and I'm going to finish my tool library. I have one tool in here, but in order to run the programs for this book, for this channel, I need to have all of these tools in here, right? So what I'm going to do is I'm going to go right now and go through that same process I did for the 1/8" tool and do it for all these other tools here, using the cutting data down here and the tool geometry in this section up here. So I'm going to do that, and why don't you go ahead and do that too, and then I'll come right back. Okay, so I have finished the tool library here, and there's a few things I noticed along the way, actually. So if we go back into the 1/8" end mill, we go to Edit Tool, and if we go to the Cutting Data section, I noticed here that I actually did have a value for vertical feed rates for the end mills. So if we go back to the the tool library description here in the appendix, I could see that for under milling feeds and speeds for the 1/8 inch tool, there's right here a feed per revolution and a plunge feed rate. So for that tool, it's 0.0004. So I can put that here, 0.0004. All right, so that's a good plunge feed rate. And then there's a plunge feed rate for all the other tools as well. So if you don't have those in there, you have to add those to there. But I think that I added all of them here. Yep. Okay. Good. The other thing I noticed was that in the appendix here, when I got to the ball end mills, there's this note right here. It says for ball nose finishing operations, multiply chip load by 1.5. So I did that for the ball nose end mills. Go back to Fusion. You can see that 1/4 inch flat end mill, you can just see it right here, actually has a cutting feed rate feed per tooth of 0.0028. But the 1/4 inch ball end mill has a feed per tooth that is 1.5 times that. Yep. The other thing that was not in the data, but is kind of good to know, like I chose a tool holder for the face mill. So if I go to edit tool there, I chose this tool holder just as like kind of a generic tool holder that can hold that face mill. But depending on the exact tool holder that you have, you may need a different one here. So for that holder, I chose the HSK63. So if you want to add that one, you can add that one. Click accept. If you have a tool holder that is not described by this one here, or by any of the ones in the sample library, you'll have to make one. And to do that, you'll have to click the plus button here, and you have to go to at the very bottom holder here, and you're gonna enter the basically the geometry of your tool holder in inches or millimeters, whatever it is. It'll add sections of it here. So in this case, it gets you can get really detailed with it. So for instance, like it said that section 1 over the top here, the height was 0.1, upper diameter was 0.5, lower diameter was 0.4 maybe. We can see how that kind of changes that. So then this lower section here, maybe the height is 0.1, upper diameter is 0.4, lower diameter is also 0.4, and this is kind of the way that you would build up the geometry of a tool holder. Now you would have to measure very accurately the side profile of your tool holder and keep adding sections in here with upper and lower diameters until you got the final actual geometry of your tool holder. And then, you'd give it a name, and then that would be the tool holder that you would use. So if you can't find any of the tool holders in the sample library, you'll have to make your own tool holders in this way. But I'm going to click cancel because I have those there. Okay, so that is the tool library as it is in the book, CNC Beginner's Guide. And so if you have this tool library, then you can follow along and you can program all of the tool paths that we're going to be doing for the projects. I'm also going to upload a file of this tool library so I can actually export it from here. I can right click and I can say export library. You can also import library. So I'm going to export it as a .tools file or something like that, and then import that library into here. If you want to get it, if you don't have a tool library but you have the file for one, you can import it that way. But we have our tool library here. So that should be it. That's making your first tool library in Autodesk Fusion. And yeah, check out the next videos to go through the project, starting with Project 1 CAD. And we're going to work through all of the setup and the CAM for project 1. See you there.